Okay, so just about the exam, you all did fine on average, 24, 25 or so out of 30 right. The exact values don't matter because at the end of the semester I take all the scores numerically to the last step when I assign semester grades. And when I do that, the average student in the class gets approximately a B. So there is, in effect, a curve at the last minute. Up to that, though, the grades go in numerically. What else? I used to have only one midterm exam, literally in the midterm. Years ago, I think back in 2009 was the last time I did that. I started having two midterms because getting some indication earlier on that you're doing well or doing poorly is useful to you all. So hopefully, those of you who did really well on this exam, great, but it's only 17-ish% of the semester score. Those of you who did poorly, but again, it's only 17-ish% of the semester score. It's in many respects sort of a heads up on where things stand and how you're doing. So if you got questions about the problems and stuff like that, or issues that come up, come and talk to me in my office hours. And once all the makeups are over, which will be mostly done today, I will hand back the booklets. I will send you another email indicating what choices you made on your exam booklet and what the correct answers were on your exam booklet. And I'll post exams and stuff like that, but I still have to wait until I've gotten through the most of the makeups. Any questions, issues about the exam, whatever? All right. Well, back into material, I've mostly finished talking about how zero-graphic copiers work. So it's sort of the end of talking about static electricity. Electricity is kind of electric charges that are pretty much sitting there doing, not moving around all that much. We'll then get into like flashlights. The point of flashlights is because we're going to start to let charge move, and suddenly interesting things will happen. Things that I hope that you have some sense for at this point now are obviously that there is such a thing as electric charge. It has positive amounts and negative amounts. The forces between them, their opposites attract, likes repel. You can store energy in the attractions and repulsions between charges. And that we call that electrostatic potential energy. And it's what's carried by electric power to your house, and it's the form of energy that shows up and makes things happen by way of electricity. What else? Voltage. Voltage measures the amount of, it's a characteristic of a location, and it tells you that charge at that location has a certain amount of energy per charge. And energy measured in joules. Normally that's the standard unit of energy is joules, and the standard unit of charge is coulomb, so joules per coulomb, and that measures voltage. Joules per coulomb has a shorthand name. It's called the volt. I'm not sure I've ever said that in class, which is kind of horrifying to me, but that's the way it is. So that's what volts mean. Volts are how many joules per coulomb you have at that location. And joules per coulomb, voltage can go negative. If it's negative, it means that positive charge at that location actually has less than no energy. You have to drag the positive charge away to get it off into the distance. It doesn't have energy stored. It's sort of got a deficit of energy. You have to pay it back to get the charge free. What else? Differences in voltage give rise to electric fields. So electric fields are this other way of looking at forces on charge that electric field pushes on charge at any location in space where there is an electric field. It's not zero. And you can create electric fields with charges, or you can create electric fields by way of voltage differences. If the voltage is high here and low there, there is a voltage gradient between the two in some form or other, and that means there's an electric field between the two, and it points from the high voltage to low voltage. It loves to push positive charges that way. All right, so it's all rehashed stuff and tedious, but it'll come back again when talking about flashlights. So, flashlights. It's the simplest of the electric, electric circuits, electric structures. And so a question to ask you here, you guys are, well, you're almost sort of post-transitional. Very few of the flashlights that you encounter these days have incandescent bulbs, the Edison-style bulb that gets hot, that produces heat because of temperature. This is one, right? So that bulb, that's producing heat because as electricity goes through it, it gets hot and it glows with its own thermal radiation. You rarely see those anymore. It's sort of, okay, when I started teaching this course, that's what there were, and now they're almost gone. The other kind of light source that's around are these ones that have an LED in them. This thing. Well, LED is short for light emitting diode. Light emitting, not so mysterious. Diode, what's that? We'll deal with that shortly. An LED, light emitting diode, is an electronic device as opposed to an electric device. That maybe not everyone may agree with that distinction, but electric stuff I view as things that where electricity moves around, so it's not static electricity. Electricity is moving around, but there is nothing very sophisticated in the system that really cares about the fact that the electricity is being carried by electrons, as opposed to just any old electric charge. Electronics now is aware of electrons, and it begins to notice what's carrying the electricity, that being electrons. And an LED is an electronic device. It knows about electrons, it cares about electrons. The old-fashioned incandescent light bulb, it's an electric device. It didn't care about electrons. It just cares about electricity. Cares about electricity. So anyway, long harangue about that. But come back to this question. The question says that if you take a flashlight, and I actually have two of them. I have an old-fashioned, old-fashioned as in 10 or 15 or 20 years old, flashlight with an incandescent light bulb that gets hot. And I got an LED flashlight. It produces light without, in principle, without getting anything hot. In practice, some stuff gets a little warm. Anyhow, if you reverse the batteries in these two devices, you all have seen the batteries inside, right? You take it, you open up the flashlight, and it's got, remember D batteries, the big guys? If you take both batteries out of this, there are two of them in there, and you reverse them, put them in backwards, will this guy still work? And the other question would be will the other one still work? Assuming that they go in properly and make electrical contact, so it's not an issue of like you didn't get them in right. Will this turn on when I flip the switch now? It's got the batteries reversed. I'll ask it like this. How many think that this will turn on when I reverse the batteries? How many think that it won't? Because the vast majority are going for won't. Works just fine. As I suggested earlier, this, because it's got an incandescent light bulb in there, just something that gets hot, doesn't care about electrons. It just cares, is there electricity going through me? And it's indifferent to which direction electricity goes. So we'll see that flipping the batteries did have consequences. The electricity is actually traveling backwards through that flashlight bulb, but it doesn't care. It's completely indifferent. On the other hand, if I do the same thing for this, it's working now. If I take these guys out, I'm not sure. Okay, it's got D batteries in, same as always. I'll flip them around backwards. Backwards. How many think this guy will work? How many think it won't? Right. Dead as a doornail. Because this is using light-emitting diodes, LEDs, and they are very sensitive to which direction electricity goes. They absolutely want the electrons to come into them from one end and leave through the other. You send them backwards, and actually they don't even let the current flow. A current being the movement of electric charge, we'll see. They don't let anything move. And that actually shows up in the very name, diode. A diode is a generic name for an electronic device that carries current only one direction. It will allow the charges to go through one way but not the other, and I now have to pin down the labeling of the charge. But now we're back in business. I put the batteries back in the right way. It's happy. So you are used to having a lot of devices that if you put the batteries in backwards, nothing happens. Those are electronic devices. They all do care about the direction in which electricity moves. There are still many devices that don't care. Certainly old incandescent light bulbs don't care. Toasters don't care. The heating element in a stove or oven doesn't care. Not too many, but it's those things, particularly things that just make heat, just get hot. Okay, so anyway, this is just an indication that there's some complexity in our future. We will get to LEDs, not today, but down the road. So some observations about flashlights. They emit light when you switch them on. And that comes about because a small component within the flashlight gets, if it's an incandescent light bulb, gets very hot, so hot that it begins to glow with thermal radiation, which is a topic for the other semester. But you've all seen it. Things that get very hot begin to emit light. That's true not just of a flashlight bulb, but of glowing coals in a fireplace, or the filaments of a toaster. They get hot enough, they glow red. That light isn't a coincidence. That is the thermal radiation coming off of a hot surface. And if you get the surface hotter than a toaster can handle, it will glow not just red, but into the orange, into the yellow, and it starts to look like an incandescent light bulb, which basically glows as brightly as it can without, it gets as hot and therefore as bright as it can be without melting too quickly or basically falling apart too quickly. Alas, that's not very hot. If it got as hot as the sun's surface, it would have the color characteristics of the sun's surface. That's unrealistic for any solid material on Earth. So they go up there trying to get as hot as they can, but it's only about half the sun's temperature by a certain measure. Anyhow, okay, so you make a hot thing. Brighter flashlights often have more batteries. The choices of batteries are a complex issue, but in general, the physically bigger batteries have more something in them, and in fact, it's typically more energy stored in them. And that means that they can be brighter, or they can last longer, or it's actually some sort of product of the two. The overall amount of light that comes out of a flashlight is related to the physical size of the batteries, also to an extent to its chemistry, but bigger batteries typically have more energy in them and can do more. Flashlights glow dimmer as their batteries age. That's certainly true of the incandescent light bulbs. We'll see that the batteries themselves are pumps for electric charge. They add energy to electric charge, and therefore they move charge from low voltage to high voltage. So that's the first time I'm saying that, but we'll see that over and over. So that batteries move charge from low voltage to high voltage, they're giving the charge energy. Because remember, voltage is energy per charge. As the batteries run out of stored energy, they have more and more trouble giving charge energy, and the voltage difference they produce starts to sag. They can't maintain it anymore. They can't give every charge as much energy as they used to. And therefore, there's just not as much energy available, and the charge is going through the light bulb, for example, and it just gets kind of dim. Some of the modern flashlights, it's a little hard to see that transition. They still get dimmer. Usually they get dimmer as the batteries get deader, but sometimes they just simply wink out. You go from bright to nothing when there's just not enough pumping left, not enough energy left in the batteries to get the job done. Flashlights, sometimes hitting flashlights brighten them. We'll see that the flow of electric charges through a battery and the whole flashlight in general, anytime you've got sort of weak links in that what's called a circuit, as we'll see, that's typically a location where energy is wasted. And the energy that's wasted there isn't available to make the flashlight glow brightly. So The standard way of brightening a flashlight, at least back in the day, this kind of flashlight, when it got dim, was you'd smack it a couple times to get all the connections to be fresh and not cruddied up, and the flashlight would get brighter unless you broke the bulb and then the flashlight got dark. But okay. All right, so some questions to go through with flashlights. Why does a flashlight need a battery and a bulb? And basically, how does the energy go from the battery to the bulb? That's really the heart of the story. Okay, so the battery is a source of electric power. It's the simplest that I can think of, simplest source of electric power. There are more complicated ones that we'll come to some extent, things like electric generators or solar cells or wind turbines, which I guess are electric generators too. But anyway, there are various sources of electric power. Batteries provide electric power by way of their chemicals. They're not making energy out of nothing. They're simply using the energy that was invested in them in the manufacturing process, or that was put in when they were recharged, another possibility. So they got stored energy, and they're consuming that stored energy to make electric power flow. And I even have to define the word power, and I will in a minute. And the bulbs are consumers of electric power. So batteries are the source, bulbs consumer. We'll see that it is possible to make a battery a consumer of electric power too during the recharging process. So if you're using a battery to run the flashlight and make it glow, it's a source of electric power. If you've taken the flashlight batteries and you've put them into some electric charging unit to pack them back full of energy, they are then temporarily consumers of electric power. It's going into the batteries. The batteries are building up again stored energy. About power. I've talked about energy, which is an amount that you have. So you have a certain amount of energy, then you can give somebody a chunk of it, give them 100 joules, and now they got more energy. If you have a big store of energy and you give somebody or something 100 joules every second, it's a continuous movement. And instead of saying how much you've transferred, it's sort of how much you transfer every second, how much you transfer per time. So energy transferred per time has its own name. It's called power. And it has its own unit. So if I'm giving 100 joules every second, that's 100 joules per second of power. And the joule per second has its own shorthand name. It's called a watt. It's the watts you've heard about and you've used yourself. So a 100-watt device, like a light bulb, the old-fashioned light bulb, a 100-watt light bulb consumes 100 joules every second. Alternatively, a generator, or when you're pedaling one of the exercise bicycles, many of the modern exercise bicycles, actually, you are generating electricity, whether you know it or not. And that electricity is being turned within the device into thermal energy. In fact, you're lighting light bulbs up, but you can't see them. You're just making hot air. And a pretty substantial pedaling, when you're pedaling, it's a couple hundred watts. You'll be sweating if you're making 200 watts of electric power with your feet. You'll notice it after not very long. That's hard work. So in that case, you are investing, if it's 200 watts, 200 joules every second into this system, and off it goes and becomes whatever it is. Always thought that they should have these things so that you can power the grid and feel like a hero. Not only are you getting exercise, but you are also reducing carbon footprint. All right, so that's the idea of power measured in watts. Any questions about power and watts? And I will try. Sometimes I casually flip back and forth between talking about energy and talking about power and joules and watts. I got to try to be careful, but I can't promise that I'll keep it perfectly clean the whole way along. I will try. Okay, so what's a battery? It is a chemically powered pump for electric charge. And by pump, I've had other instructors sometimes not like the idea that I talk about a pump. A pump, if you just think of a water pump takes water from down low and squeezes it, pushes it, pumps it, actually either to high altitude or to high pressure. So you can make pressurized water with a pump, or you can make lifted water with a pump. You can send it up to the fourth floor. In these cases, the pump is investing energy in the water. The water started out with very little energy. It's down low and it's at low pressure, both of which are low energy situations. When the pump's done, the water is either at high pressure or at high altitude, both of which are high energy situations. And that water now can do things. It can run fountains, or it can go and run a hydroelectric widget, or it can come pouring down and clean your deck or something. So pumps put the energy in, and then it can do things and come back. Those two analogies, lifting the water with a pump or pressurizing the water with a pump, they're both pretty good for the whole story of electricity. You will see batteries take electric charge from a low energy situation, as in low voltage, and they pump it to higher voltage, so it comes out with more energy. They're investing energy in the charge as it goes by, and now it can do things. So it's just like it's a lot like a pump for liquid. Okay. So battery. So specifically what a battery does is it takes charge. And again, when I'm not using no modifier in front of it, we're talking about positive charge. It takes positive charge from low voltage, as in low energy per positive charge, and it adds energy to it and delivers that charge at another location at a higher voltage and therefore more energy per charge. And this is a car battery. It's a 12-volt battery. What that means is that it takes in charge at its low voltage end, which over here is marked. There's a convention which you needn't remember but is useful. There's a convention very widely used that low voltages and negative charge are marked with black, and higher voltage or positive charge is marked with red. So black and red are just, that's, for heaven knows how long that's been the case, that is the case. So I have trouble using the wrong colored cables. Right now, they're pretty much the right colored cables all the way through. This is the red end of the battery, meaning it's the positive, higher voltage and positive charge over there. And it's running through the wires, going through the light bulb, coming back. And when it returns to the other side of the battery, and I have to talk about that whole racetrack for electric charge, it returns to the negative low voltage end. The point at the moment, though, is the battery. It's a 12-volt battery, and its job, when it's acting as a source of electric power, is to take charges in at its negative low voltage terminal and pump them chemically over to the positive terminal against their will. They don't like doing this. The charges are leaving a low voltage location, which is what they like. It's typically got a lot of negative charge around and is attractive to positive charges. So the battery is taking them, ripping them away from the low voltage end and shoving them, by doing work, shoving them onto the positive end at higher voltage. How much higher? 12 volts. Car batteries are typically at 12-volt batteries approximately. It's not exact. And that means that if they take the charge over here at 1 voltage and deliver it at the other terminal at another voltage, it's going to be about 12 voltage. There's going to be about 12 volts higher at the delivery than at the source. And then that brings up the question, well, what exactly are these two voltages? Yeah, they differ by 12 volts, but is that one 0? Or is that one 333? And this one's 12 more than that? It depends on the situation. The absolute voltages often don't matter, and in this situation, they don't matter at all. So the exact voltage of that point there, I'm not sure. It's probably about 0 volts, give or take. it would depend on, if I connected up to that big static generator, the whole thing could go to some crazy voltage. But what I can say is that if that is 0, that's 12. And if that's 48, that's 60. It's 12 volts more. The exact voltage depends on how much electric charge there is around here or there and everywhere. Really complicated and not important. Is that okay? Or questions about that idea? So the point is, this guy takes the charge, carries it chemically over there, and as long as the chemicals are able to function and get the job done, it will keep moving charge from one to the other to ensure that there is a 12 volt, this is 12 volts higher than that. And right now, it has done the job. It has moved electric charge off this one onto this one and accumulated positive charge at this side and an absence of positive charge on that side to the point where we've got a 12 volt difference between those two. And if it continued to move charge, that would be a bad idea for it, because as it took more positive charge off the negative terminal and deposited it on the positive terminal, the voltage difference would increase. It would have moved more charge, more positive charge on the positive terminal, which makes it, packing it tightly there, adds energy to it per charge, and taking it away from the other side adds energy to it per charge, but of course it's a negative charge. So the battery has a self-limiting characteristic, that it moves charge only when doing so increases the voltage difference across here up to 12 volts. Once it gets to 12 volts, it stops moving. The chemistry basically says we've moved all we can handle. The next charge that we would move would take the voltages too far apart. The chemicals can't do it anymore. The pump basically bogs down. So it tries to maintain 12 volts of difference. And since the charges are just sitting there on the terminals, positives on this side, negatives on that side, pumping more will cause the voltage to increase more and is a bad idea, and the chemicals won't do it. If I give the charges an opportunity to leave the positive terminal and go back to the negative terminal, they'll do it. And once that happens, the battery will kick back into gear, noticing that, well, we're losing positive charges on this side and gaining positive charges on that side. That reduces the voltage difference between the two ends. And now the chemistry is able to move charge again. So the battery essentially turns on whenever you start letting the charges go back. And I can do it right there. I'm now letting them go back. They're rushing through the wires, through the light bulb and back. And the battery is working again. Now the battery stopped. All right. Questions at this point, just to make sure I'm not wandering off without you. What else do I want to say here about batteries? So batteries use a chemical reaction, really, an electrochemical reaction, to move charge from the negative or low voltage terminal to the positive or high voltage terminal. They develop a certain voltage difference between the two. And rather than just calling it a difference, I'll call it a voltage rise, meaning that charge arrives at one of the terminals of the battery, the negative one, and is pumped onto the positive terminal from which it leaves. And it enters at low voltage and it leaves at high voltage. That's a rise in voltage through the battery. So voltage rise. This battery is providing a 12-volt voltage rise. And voltage rises are associated with being sources of electric power, because the charge is coming in with low energy per charge and leaving it with high energy per charge, having picked up energy per charge by way of that voltage rise. All right? My silly little analogy, just trying to make sure this is as clear as it can be and without being too horribly either pedantic or patronizing. If the battery is all full of energy, right? Chocolate bars, okay? And if you want to pick up some of that energy, you bring along an electric charge, as in my little truck, and the truck goes in the battery. It picks up 1, 2, 12 units of energy per charge. That's the voltage rise. energy per charge. It goes out, it goes through, there's a start button on this baby somewhere, but I forget. And it makes stupid noises and blinks its lights, but I won't do that. So it goes through here. If this is on, it travels along through the wires, it drops off its energy per charge in the light bulb, and then it goes back to the battery to pick up more. And the reason for doing, okay, the silly analogy story is, this whole structure, which I'm considering to be an exposed, exploded flashlight, just the pieces of a flashlight all laid out for you to see. Battery, light bulb, wires, that's what's in a flashlight, a switch. That's really all there is. The point of this is that the energy is being obtained from the battery and delivered to the light bulb. It's being delivered, and I'm walking all over my own questions, but it's being delivered by the movement of electric charges. The point of having electric charges in this story is only for delivering energy. You're not delivering electric charges to the light bulb, you're delivering energy to the light bulb. The light bulb doesn't care to have electric charges and accumulate them. It's not a collector of electric charges, it just wants energy. So electric charges act as carriers of energy. They pick up energy in the battery, they go through the wires and the switch, and they go into the light bulb where they drop off the energy. Light bulb lights up, and the electric charges then go back to the battery to pick up more energy. So in that respect, this kind of arrangement where energy is carried to the light bulb through one wire and back to the battery through a second wire is a little different than water delivery. In your house, you have electric power delivery and you have water delivery, and they're different. How? Water shows up with a substantial amount of energy in tow, too. It's pressurized, or it's high. It's got the capacity to do interesting things. You open the faucet and it sprays out, or the shower, it sprays out. That's energy in the water. But you actually do want the water delivered. You don't just want the energy the water's carrying, you want the water. You drink it, you do whatever you want with it, you wash yourself with it. And you don't return it to the water company. They don't want it back. Electricity is different. You're not trying, you want the energy being carried by the electricity, but you don't want the electricity itself. You're not collecting it either. So you have electricity come to you through one wire. You get the energy out of it, and then you send it back to the electric company through a second wire. So all electric power delivery processes involve at least two wires. Water delivery, one wire. It's just a pipe. You know, one pipe's good enough for water delivery because you actually want the water. You need two wires for electric power delivery because you don't want the electric charge. If it accumulates, it makes lightning bolts and stuff. It's not a good thing to collect. So you want to send it back to get more energy. Is that okay as a concept, or questions about that concept? The consequence of that arrangement is that electric power is almost always delivered by way of circuits, where a circuit has the meaning that it's a loop, it's a full trip. Electric power is provided at one end of the circuit and consumed at the other end of the circuit, and the charge makes the full trip through two wires. That means in general that if you want electric power to be delivered to something, it's going to have two wires in it somewhere. Relatedly, the danger in getting involved in electric power yourself with your body by accident is typically, it involves two wires as well. Touching one wire, not so bad. Touching two wires, often a problem. Yeah?
Why don't tasers kill you?
Why don't tasers kill you? And tasers have two wires, right? They have two pins in a taser. And so the charge goes in one and comes out the other. There's specific details. They try not to make a circuit through the parts of you that are most vulnerable, which is your heart. Your heart is susceptible to rhythm problems if electricity runs through it. So a shock in which power goes in one hand and out the other is particularly dangerous. A shock in which power goes in one part of your hand and out the other part of your hand hurts your hand, but it's not so dangerous to you in terms of life and limb. Nonetheless, people do occasionally get killed by tasers. They're very high voltage. I'm not quite sure the details of how they deliver the power, but mostly you don't want it going through your chest. Is that okay? Yeah, Aaron?
How does amperage play into this?
How does amperage play into it? So in the delivery of electric power, right now I talked about voltage, and voltage being the amount of energy, electrostatic potential energy per charge that's picked up in the process of going through the battery and is constantly available to be dropped off as the charge returns back through the circuit to where it started. Amperage, which is equivalent to saying what's called electric current. Electric current measures how much charge moves past a point per second, per unit of time. So when I have my little trucks traveling around the circuit, they pick up some chocolates and going through there, they go by, and another one's going through, picks up, it's going by. Current measures how many trucks, how many electric charges go by per second. So in the delivery of electric power, two things matter. One thing that matters is how much energy each charge is carrying. Energy per charge, that's voltage. So the voltage here matters. I mean, I have to pin this down a little bit. The more voltage there is around, the more energy each charge is carrying, so the more energy is dropped off. So if all things are equal and you simply increase the voltage, for example, the battery, the amount of electric power going through the circuit will increase proportionately, more or less. The other thing that matters, though, is how many electric charges are going by each second. If you have only one per second, it's only dropping off, a couple a certain amount of energy per second. If you have two going by per second, twice as much energy per second is showing up. So it will turn out that the power that the battery is providing and the rest of the circuit is consuming is going to be the product of two things. The voltage rise in the battery, which is how much energy it gives to each passing charge, and the current in the circuit, which is how many charges per second go through the circuit. It's both of those. So voltage, energy per charge, it's how chock full each charge is with energy. Current is how many charges are going by each second. Is that okay? Is an idea? They both matter. The product of the two gives you how much energy is being taken through each second, which is power, electric power. So back to Aaron's question initially, how does current play into this? Little currents of little electric currents, such as the current that would flow through me each time I put my hand in front of the static generator and got a little spark hitting me. Yeah, it's dramatic, but it's a tiny current, meaning not very many charges moved. Each charge has a huge amount of energy, but there are not very many charges. And because there are not very many charges, it's not very dangerous. The amount of charges, the current flowing through you when you get a shock matters a lot in terms of its danger to you. And I think last I knew, the rule of thumb was you don't want more than 30 milliamperes, and I'll define the ampere in a minute, flowing through your heart. That's really dangerous. So if you can keep it away from your heart, great. And if it does go through your heart in that area, you want a dinky little current, not many charges per second. The current matters. Is that okay? So what is an ampere? The unit, it's the unit of current. And where does it come from? Well, we already saw the unit of electric charge is the coulomb. That's just, the convention has been that way forever. Well, long enough. And where did volts came from? A volt is a joule of electrostatic potential energy per coulomb of charge. So if the charge is sitting at this point, this location on the battery, this is a 12-volt location, that means that every coulomb of charge I take away from that point will carry with it 12 joules of energy. 12 joules per coulomb, that's 12 volts. So that's voltage. And the current, which is the other thing to talk about, the current, if you take charges away, you would measure how many charges you're taking every second, and you would measure it in the standard units of coulombs. So a current of charge could be measured in coulombs per second. How many coulombs are you taking per second off that point by way of this wire? And 1 coulomb per second is a perfectly good measure of current, and it's given it, again, its own name. It's called an ampere, or an amp for short. So 1 amp means a coulomb is flowing past a point in space or location in space every second. And when I close this switch here, let's see, this guy is it's an 80-watt bulb. That means it's about 7 amperes of current flowing through the circuit. Now, how do I know that? It's a 12-volt battery, and this light bulb claims to be it is a 12-volt light bulb, believe it or not. It's a 12-volt light bulb. That's what it wants. And when it's supplied from a source at 12 volts, it consumes 80 watts of electric power. So I'm calculating backwards. How much current would it take to deliver 80 watts when the current is supplying charge at 12 volts and taking it back at 0 volts? So to flesh out the whole story here in front of you, what you're seeing, and actually I can turn on this gadget, will in principle show you current flow. Is it going to do it? It's not showing me anything. No lights. Oh, there it is. Can you see the little red lights moving? I can zoom in on this. See the little red lights moving here. So it's simply a display showing you the movement of what's called current. And if I break the circuit so that it's not a complete loop, the current stops flowing. And now it's flowing again. And so those little red lights are an alternative to having my little trucks traveling around this loop. So the charges are picking up energy in the battery. They're coming out of the battery at its positive or higher voltage terminal at 12 volts, meaning that every coulomb we take from here has 12 joules of energy. That charge is moving it through the wires to the light bulb, where it's entering the light bulb still at about 12 volts. More details on that later. And then it leaves the light bulb at about 0 volts. It's lost all of its electrostatic potential energy. The missing energy isn't gone from the universe. It's became the light and heat that are operating the light bulb. So the charges are going through there, dropping off their energy, and then returning to the battery to pick up more energy. Around and around they go. And if any break in the circuit prevents the continuous movement of the charge, it starts piling up on the various ends. There's positive charge piling up on this piece of the switch, and there's negative charge piling up on the light bulb in this part. And they can't get together because they're electrically insulated there. They can't continue to move. So the flow of current stops. All right. Questions at this point? What I should talk about here for a second, though, is I'm talking about the flow of charge through this exploded flashlight, exposed, deconstructed flashlight. And when I talk about movement of charge, I'm assuming it's positive charge. If we think back to the story of electrons and protons, the actual charged objects that are part of this system, the only real charges that are present here, things that actually have charge on them, are the electrons and the protons in these components here. And electrons are negatively charged by virtue of Ben Franklin's unfortunate choice. What does that mean? It means that when I'm waving my hands here and saying that this battery is taking charge, which is to say positive charge, off the negative terminal, pumping it to the positive terminal, and then having that run through the rest of the circuit, what's really happening there are essentially there are no mobile positive charges in this structure. The positively charged thingies are the nuclei of atoms, and they're not going anywhere. It's very hard to make the atoms within solid materials, which is what's over here, to make the positive charges in the atoms move. They're pretty stuck in place. What is actually moving is the electrons. They're very mobile in many situations. There's a little bit of positive charge movement inside the battery, but that's another story, because there actually is liquids in there. So, when I'm saying that positive charge is arriving at the negative terminal, is pumped by the battery's chemicals to the positive terminal, and then runs through the wires, and then dropping off energy and returning, what's really secretly happening is electrons are going the other way. And it's very hard to tell a difference. Franklin couldn't tell a difference. Most people couldn't tell a difference until the 20th century. People started to be able to tell, oh, it's actually negative charges making the movement, not positive charges. And so what's really happening here is electrons are leaving the negative terminal here of the battery. They're going through the wires, opposite to what I've been claiming, because they're carrying negative charge with them. This all works out. They're going backwards through these wires. They're going into the light bulb and going from low voltage in the light bulb to high voltage in the light bulb, which electrons like. They are negatively charged. They're attracted to high voltage. They love to go there. So they go there and drop off energy. In going from low voltage to high voltage, electrons go, wow, this is great. Drop off energy, light bulb glows, and now these high voltage electrons work their way back to the battery, which pumps them from high voltage back down to low voltage. They're negatively charged things, and it's hard. You have to do work on them to shove them back to low voltage, because there are lots of negative charges there. So the point is, physicists and scientists and engineers long ago gave up trying to follow the flow of electrons in most situations, except for electronics. Electronics, we've got to follow the electrons. But in most situations like this, like electric power delivery, making your flashlight work, they create a fiction. They say, let's not follow those electrons going around, because electrons, they're carrying negative charge. Everything's flipped. It is analogous to an economic system, a financial system, where the only bills that are available are all printed in negative denominations. I've done some of this before, that you can go purchase things and make money. You can get your salary. You can go spend it. It can all be done with negative dollar bills. It's just nasty to think about, because when you go in to get your paycheck, you get your net worth has to go up. So how do you do that? You give your boss negative dollar bills, which reduces your debt, and you now become more wealthy, and your boss receives the negative dollar bills and becomes poorer as a result. So it's really awkward. The whole thing's a mess. So instead of doing that, we just say, forget the electrons. Let's watch some fictitious positive charges going through the system. Life is simple, works nicely. The battery takes those positive charges in at low voltage, delivers them at high voltage, runs the system, and goes back. The charges go back to pick up more energy. And that's how we'll work. We'll ignore the electron flow until we absolutely have to, and just watch these fictitious positive charges going through the circuit. All right, we'll stop and continue on Wednesday.